Our video today is to calculate the position x meters at time t seconds of a particle moving in a straight line. It's given by x equals negative t minus 1 all squared times by t minus 4. And the first part of our question is to sketch the particle's acceleration versus time, their velocity versus time, and the position versus time graphs. So to do this, let's actually start with the position versus time graph, and time can't be negative, so I only need the positive t-axis, and the x value or the position is on the vertical axis. The first thing I'm going to do is I'm going to find out what the x-axis intercept is. Now, a bit confusing, the x-axis here is actually our vertical axis, so I need to substitute in t equals 0. So my x-intercept is at t equals 0, which gives me 0 minus 1 all squared times by 0 minus 4, and then that equals negative positive 1 times negative 4, which is equal to positive 4. So I can put that point on my graph. I'm going to say that that's 4. Then my t-intercepts on the horizontal axis are going to be when x equals 0, and that's going to look like this. So I have 0 equals negative t minus 1 all squared times by t minus 4. And if I use the null factor law, I get the two solutions, t equals 1 and t equals 4. So I'm going to call this point 1 and this point 4. So we've got 0, 4, I have 1, 0, and 4, 0. And because this graph is a cubic, so if we look at the original expression, I have a squared and a power of 1, so it is a negative cubic. When I draw my negative cubic, it will have a turning point at that first axis intercept, and it will look something like that. Okay, let's move on now and find the velocity versus time, because if I want to find this turning point here, I'll need to differentiate the position, and when I differentiate the position I get velocity. So let's do the derivative now and find dx dt. Now there's two ways I can do this. The first way is I can use the product rule. So if I use the product rule here, I'm going to keep the first bracket and then differentiate the second one, which is t minus 4. The derivative of t minus 4 is just 1, plus I'm going to keep the second bracket, which is t minus 4, and differentiate the first one, which will be negative 2 times t minus 1 to the power of 1. A little bit of tidying up here, I get negative t minus 1 all squared minus 2 times t minus 4 times t minus 1. And then I could expand the brackets here. I think I might actually expand the brackets on this one. So that'll give me negative t squared minus 2t plus 1 minus 2 times t squared minus 5t plus 4, which is negative t squared plus 2t minus 1 minus 2t squared plus 10t minus 8, which is negative 3t squared plus 12t minus 9, which if I bring out a negative 3 outside the brackets, I get t squared minus 4t plus 3. Okay, so if this is the change in x with respect to t, that's equal to the velocity. Now, if I want to find the turning points from the first graph, that will be when the velocity equals 0, and that will also equal the x-axis intercepts for my velocity time graph. So the t-intercepts of my velocity time graph is when v equals 0, and from here, so I'm going to write -3 times t squared minus 4t plus 3, divide both sides by the -3, t squared minus 4t plus 3, and then I can factorise that, t minus 1, t minus 3, and so we get the velocity is equal to 0 at t equals 1 and t equals 3. Now also, if I want to find the velocity axis intercept for my second graph, the velocity intercept is going to be when t equals 0, and that's going to give me -3 times 0 squared minus 4 times 0 plus 3, which equals -9. And I could have seen that from up here at this equation. So let's draw our velocity graph now. We know it intercepts the velocity axis at -9, so let's just call this -9 down there, and it also intercepts at 1 and at 3, and this graph is a quadratic. It's a negative quadratic for velocity, so I'm just trying to work out how I could possibly have all of these things come together. Negative quadratic has to be upside down. It's going to look like that. This is at 3, 0. I should have put that 0, 9, and then that point there is at 1, 0. And it makes sense then as well that this point here is at 3 something. We don't know what it is yet. And this point here is at 1, 0. We already had that coordinate written down, but I'll rub it out from the top there because it's a little bit buried under the graph. Okay, so now that we know what the turning point is, let's go ahead and find out what the y value is when t equals 3. Or what the, I shouldn't say the y value, find out what the position is when t equals 3. So let's now change colours, and in this graph, let's go a little bit further and find x of 3. And that'll equal -3 minus 1 squared times 3 minus 4, which equals -2 squared times -1, which is equal to +4. So let's get rid of that question mark, put a +4 up there. Nice. So we have now got the full graph for position. We've got the best part of the graph for velocity, but we don't have this maximum here. Using symmetry, I know it's got to be halfway between 1 and 3, which is at 2. Let's substitute 2 into the velocity formula to find out what that maximum value is equal to. So let's find v of 2, which will equal -3 times 2 squared minus 4 times 2 plus 3, which is -3 times 4 minus 8 plus 3. which is negative 4 plus 3 is negative 1. Negative 3 times negative 1 equals 3. So that's 3 there. Nice. Okay, so we've got the velocity time graph. Now I need to find out the acceleration graph. And to get the acceleration graph, I need to differentiate v in terms of t. And to do this, I'm going to use this formula. Not that formula actually. Let's go back a step. I'm going to use this formula up here because it's already expanded, and that makes the differentiation just a little bit easier. So I'll get negative 6t plus 12. Alright, so now we've gone from a cubic to a quadratic to a linear graph, and all of that makes sense when we start considering what we know about differentiation and functions. So here, this has a y-intercept. Now it won't be y this time, I keep doing that. It'll be the acceleration axis intercept, and it will have a gradient of negative 6. So, and I know from my previous graph that the acceleration is 0 at this turning point for velocity, and that occurs at 2. So let's call that 2. Let's call this value 12, and here's my acceleration graph. And we probably should label the axes, so let's call that's my acceleration axis, that's my time axis. Okay, now that took a long time, but we have all of our graphs and now all of our information to hopefully answer the other parts. So part B, this was part A. For part B, at what times is the particle's velocity 0? Well, the velocity is equal to 0 at 1 and 3 seconds. So let's actually go ahead and write that straight in here at 1 and 3 seconds. What is the acceleration of the particle at these times? Alright, so we got the acceleration of the particle. Here's our equation for acceleration. So acceleration is given by negative 6t plus 12. So at 1, acceleration is equal to 6 meters per second squared, and at 3, the acceleration is equal to minus 6 meters per second squared. So let's write them in at the top at plus and minus 6 meters per second squared. Or I probably should say, we could formalise that a little bit better, I think. Let's say A of 1 is equal to 6 meters per second squared, and A of 3 is negative 6 meters per second squared. So that's part C. Part D, determine the maximum velocity and the time that it occurs. Alright, we have that straight on our graph here. The maximum velocity occurs at 2 seconds and is equal to 3. That's straight off our graph. Got to find a place to fit this in. So my maximum velocity, v at 2 seconds equals 3 meters per second, and that is the max velocity. What is the particle's displacement after 4 seconds? So part E, here's the displacement after 4 seconds. Displacement equals 0 meters. And what is the distance travelled by the particle in the first 4 seconds? change colours for this. So remember, distance, I have to add up all of the changes in a vertical direction. So I travel down 4 meters, then I go up 4 meters, and then I go down 4 meters again in the first 4 seconds. So I need to have 4 plus 4 plus 4, because remember, distance, we don't care about what direction it is. So the final part here is 4 plus 4 plus 4, 12 meters in 4 seconds. Now I'm not super happy with how I've set out my workings there, but you can see how I can use those graphs and all of the details of the graphs to quickly calculate a lot of other values. So if you're ever stuck and not sure how to proceed, maybe a technique you could try is to draw a graph. And that's the end of our first example.